Hello everyone. Today we are going to discuss about counters. There are two types of counters, synchronous counter and asynchronous or ripple counter. So first we will see what is counter. Okay, counter, it is a sequential circuit and it is a digital circuit for counting the number of pulses given at the input. Okay. Counter, widest application of your counter, like in counter we will be using the flip-flop, and you will be using a group of flip-flops for the counter. If it's a 2-bit counter or 3-bit counter, accordingly you will be using a number of flip-flops. So all the flip-flops will be connected to all the flip-flops are connected to a clock signal. So the circuit diagram of your synchronous counter and the asynchronous counter is given here. The synchronous counter, so this counter is nothing but a 2-bit counter. Both the counter, whichever is projected here, the synchronous and the asynchronous counter is a 2-bit counter, So the number of flip-flops required for storing these 2 bits is said to be your either it can be any of the flip-flops. Okay, the number of flip-flops required for storing 2 bits will be 2. Okay, will be 2. Hence, we are using 2 flip-flops, T flip-flop here and JK flip-flop here in case of your synchronous counter. And T flip-flop for your asynchronous counter. So, asynchronous counter and the synchronous counter. What is meant by synchronous counter? See, you have 2 flip-flops. You have clock signal. This is your clock. For your flip-flop, you have 2 flip-flop, 2 clock signals. All the clocks will be tied together. All the clocks and will be tied, and it will be given from the same clock generator. Okay, all the clock will come from the same clock generator circuit, meaning both the flip-flops are synchronized to the same clock or synchronized to the same clock. Okay, this is said to be synchronous counter. This is said to be synchronous counter. Whereas in asynchronous counter, again this is a 2-bit counter. Okay, again this is a 2-bit counter. Only the first flip-flop, usually this the first flip-flop, wherever this is, if it is A and B, this A is said to be your LSB bit and B is said to be your MSB bit. Okay, MSB bit. So I said it's a 2-bit counter. So 2-bit counter, it can take 4 possible combinations, namely 0, 0, 0, 1, 1, 0, 1, 1. This will be the state transitions. Okay, this will be the number of states. Number of states will be 4. Number of states will be 4, and the transitions may be from 0, 0 to 0, 1, 1, 0, 1, 1 if it's an up counter. If it's a down counter, from 1, 1 to 1, 0, 1, 0 to 0, 1 and 0, 0, 0, 1 to 0, 0. This is your down counter, and we will also have up down counter. We will also have up down counter. For up down counter, we will be using a 3rd bit, a control bit, 1 bit we will be using, and we will be designing in such a way. If the control bit is 1, if it is 1, it will be an up counter. If it is 0, it will be a down counter. So coming to the asynchronous counter, only the least significant bit flip-flop, significant bit flip-flop will be having a clock from the clock source or the clock generator, will be fed with the clock generator. And the successive bits, it's a 2 bit, so we are having 2 flip-flops. If it's a 3 bits asynchronous counter, you'll be having 1 more flip-flop, and for n bit counter, you'll be having n number of flip-flops. Okay, according to the 2 power n, this n to this n value, you'll be having number of flip-flops. So now the second flip-flop, the MSB flip-flop, will be fed from the output of the first flip-flop or the preceding flip-flop. Now this is the first flip-flop, this is the second flip-flop. Hence I am saying that output of the first flip-flop will be fed to the clock source of your flip-flop. And in each and every case, every other flip-flop, okay, the clock source will be fed from the, it will be fed from the output of the previous flip-flop. Okay, output of the previous flip-flop. So as I said, Usually, asynchronous counter uses your JK flip-flop and T flip-flop. JK flip-flop should be used in the toggle mode, meaning toggle mode of JK flip-flop is nothing but when J and K are tied together, and your JK flip-flop will be in your toggle mode. So, JK flip-flop in toggle mode, what is the toggle mode? When J and K are tied together and if it is given high, okay, if it is given high, output will vary from 0 to 1 and 1 to 0, like that for every clock. For every clock transitions, your output may vary from 0 to 1, 1 to 0. If my previous input is 0, my current input of my during my next clock will be 1, and the next subsequent clock will be having 0. That is said to be your toggle mode. Usually, asynchronous counter will be designed by using JK or by using your T flip-flop. Okay. So, synchronous counter, I may use any counter for designing because all the clock are synchronized with respect to the same clock generator. So, whatever input that I am giving according to the design, you will get the output. This is the basic difference between your synchronous and the asynchronous counter. We have only one clock generator. The subsequent, in case of asynchronous counter, in subsequent flip-flops, the output of the previous flip-flop will be fed to the subsequent flip-flops as the clock, and based on the clock, so you will be having a delay in the output of the second flip-flop here. In synchronous counter, whenever you are applying a clock, all the flip-flops will be triggered at the same time, meaning you will be giving clock at the same time. So, the response will be faster in case of your synchronous counter. So, whereas in your asynchronous counter, it has to wait because the second flip-flop, though you are giving input to the second flip-flop, it has to wait for the first output. It has to wait for the first output. Only if that is only if your input is available, clock input is available, your second flip-flop will respond. So, there will be a time delay. That time we cannot judge. We cannot judge what can be the time. Hence, the name it is said to be the asynchronous counter. So, coming to the difference, I will just tell whichever is suitable at this stage. Okay, only those differences I will focus now. Clock input, as I said, all the flip-flops are not clocked simultaneously. Okay, that is your asynchronous counter, where all the flip-flops receive clock signal simultaneously. Okay, and how will be your connection pattern? Output of your preceding flip-flop is connected to the clock to the next flip-flop. That is your asynchronous counter. Whereas there is no connection between your output and of the preceding flip-flop and the clock of the next one. Right? Your output is not connected to the clock in case of your synchronous counter. Output is not connected to the clock of the next flip-flop in case of your, it is not connected to the clock of the next flip-flop in case of your synchronous counter. Okay. And this and all I will tell during the due course of time. Frequency of operation low because of long propagation delay. As I said, it has to wait for the clock or it has to wait for the output of the preceding stage because that is going to act as a clock for the next stage. So, low because of the long propagation delay, maximum frequency of operation, and high due to shorter propagation delay because all the clocks occurs at the same time. So, immediately your flip-flops will respond once it after receiving your input as well as the clock, immediately your flip-flops will respond in case of your synchronous counter. Okay, this is the major difference. Okay, so propagation delay is nothing but what is the time delay for the bit to change, meaning for the transition in the state. Okay. So, propagation delay, it is much shorter than that of your asynchronous counter. It is longer in case of your synchronous counter, it is less. Asynchronous counter, it is larger. Okay. This is about your difference. And I am going to continue with asynchronous counter. So, as I said earlier, asynchronous counter, it is nothing but your output of the the preceding flip-flop output will be connected to the succeeding clock of your next flip-flop, meaning succeeding clock of your next flip-flop. That is your asynchronous counter. So today I am going to discuss about 2-bit ripple counter and 3-bit ripple counter. Asynchronous counter, it is otherwise said to be ripple counter. So I am going to give an introduction of 3-bit ripple counter, and 2-bit ripple counter we will discuss about 2-bit up counter, down counter and up down counter now, and I'll just give an intro for 3-bit ripple counter so that you can design it. So what is mean by an asynchronous or ripple counter? So usually the ripple counter will be designed by using, as I said earlier, it will be designed by using JK in toggle mode or by using your T flip-flop, and only one clock pulse will be given to the LSB bit of the flip-flop. All other clocks of the remaining bits will be fed by the output, okay, of the preceding bits, that is your LSB bit flip-flop, okay. All the bits won't appear at the same time, and it is time independent. It is not time dependent, it is time independent. It is not synchronous to the same clock, hence it is said to be asynchronous or ripple counter. And before going into asynchronous or ripple counter, and in JK flip-flop, when J and K are tied together, that is said to be toggle mode. That is said to be toggle mode. And if it is given 1, see J and K, this is a circuit diagram. So J is 1, K is 1 here. So during this period of time, okay, so J is 1 and K is 1, okay, assume that if it's a positive edge triggered flip-flop, so already the clock is raised to 1, already your clock is raised to 1, okay, so you have an input, your clock is high, so your input is 1 and 1. So when your input is 1 and 1, it is said to be in toggle mode. Toggle mode means before this 1 and 1, your output Q of your JK flip-flop is 1. So toggling means from the previous output, it has to change to the next output. If it is 0, it has to be 1. If it is 1, it has to be 0, and it will toggle then and there. So the clock is indefinitely high, meaning you have a large on clock pulse. It's a positive edge triggered clock. So since it's a positive edge triggered clock, okay, so here your clock is also appearing at a long time. So the toggling happens continuously during this period. Your output is not stable. Output is not stable. It is toggling between 0 and 1 continuously, okay, with a propagation delay. This condition is said to be race around condition. This condition is said to be race around condition. This is an unstable state. Because we cannot determine the output. How to overcome this race around condition? If it's a negative edge triggered clock, okay, so negative edge triggered clock means only during your falling edge of your clock pulse, whatever may be the input, your output, you will be having a change in the output. Now this is 1 and 1, okay. So your previous input is 0. As I said, only during your negative edge, you will be having a changeover. Now you have a toggle. From 0 it has changed to 1. And again during your next subsequent pulse, because this state is over, though this is 1 at this stage, till this stage it is 1, okay. Only during the next consecutive negative edge trigger, whatever may be the input now, it will sense here what is your JK input. Now at this point your input is 0, and for J, and for K is also 0. So accordingly For J0, K0, your output will be 1 only. Continuously your 1 will be retained. Okay. If it has been a positive edge triggered, okay, positive edge triggered, so you will be having a toggling. Till here you will be having a toggling between 0 and 1. Okay. Even here, till here, right, till here. You will be having toggling between 0 and 1 as like here. This is said to be race around condition. So, the only way to avoid your race around condition in case of JK flip flop is nothing but you need to use negative edge triggered flip flop. Keep this in mind. Okay. So, let us go ahead with the 2-bit ripple counter. Okay, 2-bit ripple counter. This is a 2-bit ripple counter, as I said. So, 2-bit means we need 2 flip flops. I am using JK flip flop, J and K tied together and giving a high. So, this is said to be J and K flip flop in toggle mode because we need like that. Why we need this toggle condition? Because all the flip flops is not synchronized with the same clock. The clock of the second or the succeeding flip flops will be dependent on the output of the preceding flip flops. Hence, only in case of your JK flip flop in toggle mode or in T flip flop, you will be having change in the bit positions or change in the states in case of your counter. Okay. So, now, so we have a clock here. So, J and K is tied together and given high. So, this is your clock. Negative edge triggered the clock for avoiding your race around condition. Okay, for avoiding your race around condition. So, now this will be your first clock. Let me go ahead with Q. First output of your flip flop. Okay, of your flip flop JK. So, now this is your A flip flop and B flip flop. Assume that A and B, and usually this is your LSB bit and MSB bit. Okay, it's an up counter. So, you have 0 0 0 1 1 0 1 1. Your transition of states will be like this. It has to be like that. So, your output is QA and QB, or you can, since it is taken as Q0, I can take it as Q0 and Q1. Okay. So, Q1 will be your LSB, where for Q1 you will be given the first flip flop, you will be giving the clock, and this Q1 will be your next clock signal. This is Q0, I am sorry, Q0 will be the clock for the first flip flop. Okay, keep this in mind. So, now your J and K, J is high. Assume that J and K is tied high. Before tying it up to high position, so previous output, before this you have your previous output to be 0. Let me assume that it is having 0. Okay. Now, what you are giving? You are giving high at this time. Okay. J and K is high at this time from this point of time. So, you have a negative edge trigger. So, once you have a falling edge of your clock, whatever may be the input. So, now your input is here. Okay. Now, your input is here. So, assume that you are giving the input only, JK input is high only from this point. Okay. From this point. From this point it is high. Okay. This is your JK input 1. So, now whatever may be the previous output 0. So, it will toggle, right. So, till where? Till this point. Till your next negative edge trigger. Right. And then now again J and K is tied together continuously to high. So continuously it will be in toggle mode. So automatically it will transverse between your 0 to 1 and 1 to 0 respectively. Okay. It will be moving like this. Okay. So now this Q0 will act as the clock for the next flip-flop. So your out of Q1 for the output of Q1, okay, for the Q1 output, meaning the second output MSB, okay, for MSB, this is going to be your negative edge trigger. Okay. So now assume that till here your output is 0. Till here your previous output is 0 for the second flip-flop. Output is 0. Assume this. Okay. From this point of time, you have a toggle condition. Your clock is there. Okay. It is given as a clock to this bit. So now previous state is 0. Till your next clock, you will be having 1. Okay. Till your next state, you will be having 1. And till your next state, you will be having 0. Okay. It will be like this. So this is how your ripple counter will act. So as I said, this is going to be your MSB. So it will be Q1 and Q0. So this is MSB and this is LSB. So this is 0, 0. And again 0, 1. And this is 1, 0. And this is 1 and 1. So again it will go on and on. 0, 0, 0, 1, 1, 0. And then it will be here 1. So 0, 0, 0, 1, 1, 0, 1, 1. This is how this will act. Right? So when you write your previous state and the next state, so of my present state and next state truth table, I can even write here. So this is how I can write. So Q1, Q2 is your present state. This is my next state. And for your clock 1 will be your input. This is same as like your Q0. This one is same as your Q0. Okay. So this will be 0, 1, 0, 1. Okay. Like this I can write the state table. Okay. So let me go ahead with the down counter. Okay. Down counter. So for the up counter, I have taken the clock input from Q0. Am I right? So for the down counter, let me take the clock input from the Q0 bar. Okay. The circuit diagram of 2-bit ripple counter will be like this. So you will be having 2 flip-flops. See now earlier we took from Q0 we took the clock pulse. Now I have taken from Q0 bar the clock pulse. Okay. And the timing diagram I will draw now. So again your output will be, assume that 0 for negative edge trigger clock, always your JK, now it is tied to high. At here, from here, whatever may be my previous output, you assume that you have my previous output here as 0. So now since your JK is tied to 1, I will be having a toggling. Okay. From 0 to 1. because your JK is continuously tied high. So how will be your Q0? It's just the complement of this. When this is 0, this has to be 1, and this will be so it is just the complement. Now this will act as your clock. Let me draw this MSB. So for MSB, as I said, this is going to be the clock, and for each falling edge there will be your output transition. Assume that previously your Q1 output is 0. Now this is going to be 1 till your next clock. This is going to be 0. So now this is your MSB and this is your LSB, right? So now this is 1 1 and 1 0, 0 1 and 0 0. That is your down counter, right? So 1 1, 1 0, 1 0 1 and 0 0. So this is about your 2-bit ripple counter. If you need to design a 3-bit ripple counter, you will be having one more flip-flop. That's all. You will be having one more flip-flop such that your Q1 bar will be connected to your clock of your next flip-flop if it's a 3-bit counter. So this is your JK and this is going to be your clock. And J and K, again it is tied high and it will be given to the common output. And this is your Q2. Okay. And as like I have drawn a Q0 bar as a clock, here you need to draw Q1 bar for the clock. Will be acting as the clock for the next pulse, next bit. Okay. And then you need to extend your clock pulse here and then you need to draw the diagram. Okay. That is regarding your 3-bit ripple down counter, as well as your up counter also you will be having your third JK flip flop. So this is about your 2-bit and ripple counter, up and down ripple counter, and your timing diagram. Okay. Thank you. In the next class we will discuss about 2-bit up down ripple counter. Thank you.